Okay.
Hi, Miss Wen.
Hi. Oh, absolutely, yes. Okay. Okay, let's get this on. Okay. So when last we left, we were not doing Science 9, we were doing Chemistry 12. Yay. Okay, and when last we left, we had the reaction where we had NH4Cl on the left, and we had NH3 and HCl on the right, and we were on page 7.
Just finished page 6.
Yeah, just finished page 6, just barely started page 7. We like highlighted the 2 dots, okay? So at the beginning, we have lots or loads of NH4Cl, ammonium chloride, and we have none of the product. So what is the rate of the reverse reaction again? 0, and the forward rate is fast. So let's use that reaction there where we have, and I'm going to actually rewrite it down here so you can see it without having to go up there, NH4Cl. The forward arrow is big. The backward arrow is non-existent because there is nothing there. HCl. Okay, you don't have to write this here. I'm just writing it so that you can see it. As an upshot of this forward reaction being fast and the reverse reaction being 0, are we using up NH4 faster or slower than we are producing it? We are using it up faster than we are producing it. Hopefully that makes sense. Give me a wave if it does not make sense. Okay. Therefore, as time goes on, the concentration of NH4Cl will decrease. And if NH4 concentration decreases, what is going to happen to the number of collisions between NH4 molecules, NH4Cl? There's going to be fewer collisions. And if there are fewer collisions between reactant particles, what's happening to our forward rate? It is decreasing. Could you guys please do the same process for the NH3 and HCl? Can you do that one on your own, do you think? Okay, give that a go. Once you've got it filled in, check with your neighbors, see if they got the same as you did. Okay, so with our arrow only going forward, we are producing NH3 and HCl faster or slower than we are using them up? Faster. So as time goes on, what will happen to the concentrations of these guys? Their concentrations will? If we are making them faster than we are using them up, their concentrations will increase. So will there be more or fewer collisions between these particles? There will be more collisions. And so what will happen to the reverse rate? If there's more collisions, the rate is going to increase. So the forward rate is decreasing, the reverse rate is increasing because we are using up reactant and we are making product. All right, so we can now represent this. Yes? Oh, is it a mystery? I don't know. It will do what? Increase. Yes, I'm so sorry. I wrote it up here and then I forgot to write it in the place where it was supposed to be written. I don't know. Sometimes I do that. So now the forward rate is still fast, and we're going to show that by the arrow being quite large. Okay. It's still fast, but not quite as fast. And our reverse rate is, now it is occurring. It's occurring, yay, but it's not too fast yet. So that means our forward rate is still faster than our reverse rate. So if we put that on our graph, the forward rate started really high and now it got a little bit slower. The reverse rate started at 0 and it got a little bit faster. So far, so good? Okay. So we have a fastish rate going forward. Should make that yellow to be consistent. Fastish forward rate and a slowish reverse rate. Using that fact that your forward rate, forward rate is fast-ish. Why does it want to keep making my lines straight for me? That's unhelpful. It thinks it's being helpful, but that's what Microsoft does. It tries to be helpful and fails miserably. NH3 plus HCl. So our forward rate is faster than the reverse rate. Using that, can you please try to fill in these little doodads here? Not usually. We usually just use it for figuring things out, but we don't normally write the arrows different lengths. We use it when we're sort of learning about the rates. Yeah? Yeah. Usually we just write the arrows like this, no matter what the speed is, right? Just whatever you happen to write. Yeah, that's a very good question. Thank you for asking. I'm going to draw cards for this one because that'll be fun. Where's some of these upside down? I've gotten them all backwards-ish. So, better. Are we using up NH4Cl faster than we are producing it or slower than we are producing it? That can just go in our inbox, please. Are we using up NH4Cl faster or slower? Malaya, what do you think? Are we using up faster? Yes, very nice. And therefore, as time goes on, the NH4Cl concentration will, Abton? It will decrease because we're using it up faster. And so will there be more or fewer collisions between NH4Cl, Shiho? If you have less NH4Cl, will we have more or fewer collisions? Fewer collisions. And that means that our forward rate will be, Ella? It will be decreased. So it is exactly the same as before, right? We had a faster rate and now it is becoming slower. The forward rate is becoming slower. Second one, we are making more. Oh, I'm giving away the game here. We are producing NH3 and HCl. Are we producing them faster or slower than we are using them up, Alfred? Are we making NH3 and HCl faster or slower than using them up? Faster. As time goes on, NH3 and HCl concentrations will, Chelsea? Increase, yes. And if those concentrations have increased, will there be more or fewer collisions, Ethan? More collisions, which means that the reverse rate will, Dylan? Increase, okay? So again, on our graph, what do you think that's going to look like on our graph? The points are going to, where will they go? They're going to go like this, and then this one's going to go like this. Can you predict what will happen next? They're going to go towards each other, and eventually, what do you think? They're going to reach dynamic equilibrium. And what happens at dynamic equilibrium? At equilibrium, the forward rate, what can we say about the forward rate compared to the reverse rate? They are equal, so they should come together, okay? So let's take a look at what happens here, okay? So you're going to now draw smooth lines connecting the dots, and then you're going to draw what you predict is going to happen after we run out of dots. Just in the tray, there's great. Thank you so much. So your graph should look something like this, where eventually the two lines are really like almost on top of each other. You can draw the red one slightly, or the reverse one slightly above the, or sorry, slightly below the other one, just so you can see the different lines, but they would really overlap, okay? Which rate is the black one? Is that forward or reverse? That's forward. FWD. This one down here is our reverse rate, REV. And this diagram is called a rate diagram. On the y-axis, because it is a rate diagram, we are going to have rate. in molar per second. And on the x-axis, again, we have the progress of the reaction. Anytime we are dealing with an equilibrium system with a reversible reaction, your rate diagram will always, if the rates are not the same, they will come together. And we're going to do an interpretive dance with sound effects because it will help you remember. So this is the sound and the motion of a rate diagram. Or you can just go, if you don't want to make the, you can just go. So everyone's going to do that with me. Say rate diagram. Rate diagram. No. It's not like this. It's not rate diagram because that would look like this. Rate diagram. No. Rate diagram. Okay, those two rates come together always. Okay? In a closed reversible system, at constant conditions, the forward and the reverse rate will always come together until they are equal. Okie dokie? I mean, honestly, I often write things down that you don't have to write down. You can just be like, and that makes sense. Right? No. But we do have a demonstration today. I should make sure that my kettle is boiling. It's not. Here we go. Why do we have to reach equilibrium? It's not that we have to reach equilibrium. It's that over time, what happens is that you're going to be making more products. So your product is going to increase and your reverse rate will increase. Yes. And your all reversible reactions in closed systems at constant conditions. Okay. If you open the system, all of a sudden things are escaping and that's all bets are off. If you start changing the temperature or the volume of the container, that's going to change things. So it has to be closed and the system has to be a reversible reaction. It can't be a one-way reaction. Okay? Yeah.
So there's no way for us to manipulate a reactor to make it go to equilibrium faster.
We can, yes. A catalyst added to a reaction speeds up both the forward and reverse rates, so you will reach equilibrium faster. Yeah? And let's just mark the point. Where is the point on this graph where we have reached equilibrium? Where have we reached equilibrium? I'm going to start moving my pen and you're going to tell me when to stop. Yes? So here is where we reached equilibrium. And Eq'm is equilibrium. Okay? Eq'm. I'll make that look more like an M. All right, we're not going to watch this video because it's just exactly what we already talked about. There are some exercises here that you will do for homework, but not right now. And we're going to go here. Again, we're not going to watch the video. If you were doing this on your own, you would watch the video, but we're not going to. So when last we left our system, we had reached equilibrium. Yes? The forward rate and the reverse rate were equal. This is on page 11.
Even out.
Hmm?
Oh, it's even out.
That wasn't at all egotistical or anything, was it? Okay. Now we have an equilibrium here. Both reactions are still happening. Forward reaction is happening, reverse reaction is happening. What word do we use to describe that? What we say it is a blank equilibrium. That is a dynamic equilibrium. Because the forward and reverse reactions cancel each other out, we can say that the what type of properties remain constant?
So the second letter or the first letter?
First letter.
Observable.
Observable.
Macroscopic.
Macroscopic. The observable macroscopic properties remain constant. Now, since the rates are the same, the concentrations of the reactants and products stay constant. Just like you remember that hole didn't get bigger, the hole didn't get smaller, the concentration of products stays the same. The concentration of reactants stays the same. Is it true that the concentration of reactants will equal the concentration of the products? Will the amount of product and reactant be the same? No. Okay? So even though they're constant, it does not mean they are the same. In other words, IE, do you guys know IE? Have I told you IE? I, id, E, est. This is from Latin. And id est stands for that is. In other words, that is to say. So, in other words. So, IE means in other words. So, in other words, concentration of products does not equal the concentration of the reactants. Now, is it possible that there might be some conditions where they do equal each other? Yes. How likely is that to happen? Not very. So we just say, you know, really they don't, okay, to speak of. So for example here, perhaps we are at equilibrium, at an equilibrium. All right, here's our equilibrium here. And in this particular equilibrium, we have lots of product and not very much reactant. Okay, that is an equilibrium. Under different conditions, you might have much more reactant. This is also equilibrium. This is a different equilibrium. But in both cases, the forward rate equals the reverse rate. And the concentrations do not change. Is good? Okay. Now, what kind of different conditions are we talking about? Maybe we've changed the temperature. Maybe we've changed the volume of the container. We'll look at all of those individually as we go, all right, and how they actually affect the position of the equilibrium. So there's just a little summary here. It just says what we already said. The concentrations of the products and reactants remain constant, but that does not mean that the products equal the reactants. Nope, nope, not true. The relative concentrations does depend upon the conditions. So that would be temperature, pressure, volume, etc. And now we're just going to learn some language around this. If we have a situation, and here we're going to be describing the position of the equilibrium. If we have more products than reactants, we say the position of the equilibrium lies to the right, because we got more stuff on the right of the equation, okay? There's another way of saying this. We can say that the products are favored at equilibrium. Now, obviously, the reverse of that is also true. If we have more reactant than product, then instead of lying to the left, the position of the equilibrium lies to the, to the right. Now it lies to the left. Instead of the products being favored, the reactants are favored at equilibrium. Yes?
If it's favored, how can it be at equilibrium?
Because the position of the equilibrium sits there. We just have more of this. It just sits there with more of it than the other one.
Okay.
Yeah? Sometimes, I mean, yeah, no, yeah.
Okay.
Sometimes we use the word favored to talk about which direction is favored when it is shifting, and you might feel more comfortable with that use of the word favored. Okay? Yes.
So, like, the position means the relative?
Yes. So eventually we're going to get to a point where we do this mathematically, and we say, what is the ratio of the products relative to the reactants? Yes? So eventually we're going to get to the point where we do the math with that, and we say, here's our concentration of our products, here's our concentration of reactants, what is the ratio? And at these conditions, the ratio will be bigger, and at these conditions, the ratio will be smaller, okay? Don't worry about that if you didn't catch that. That's coming later in another section, okay? Now, we can change the position by changing the conditions. So the position changes when the condition changes. So for example, if we are at equilibrium, this is our original equilibrium. If that is our original equilibrium, and then we heat it, so we increase the temperature, it turns out for this particular reaction, that causes more product to be made and more reactant to be used up. So we start off with lots of reactant. And we finish with lots of product. So the position of the equilibrium here lies to the left. The position of the equilibrium here, this is our new equilibrium. The position, and if you want an abbreviation for position, that's position. The position of the, that's an N, equilibrium lies to the right. And that's going to depend on whether the forward reaction is endothermic or exothermic, and we'll figure out how to determine that, okay? Later. Now, if adding temperature, or sorry, if adding heat, if increasing temperature moved the equilibrium to the right, oh, by the way, we should say this process of going from left to right, this is called shifting. No, right to left as well. So we would say that this equilibrium shifts right when we increase the temperature. Another word that I'm going to introduce, so we've introduced the word shifts. Okay, and that's when it moves from one equilibrium to a new equilibrium. When we change the conditions, that also has a word associated with it. That is called a stress. So when we change the conditions, that is called a stress on the system. Okay? So new words, shifting, stress. So if increasing temperature shifted the equilibrium to the right, what do you think decreasing temperature will do? It will shift it to the left. So if we start with lots of product and we cool it, the equilibrium does what? It shifts. Okay, and so we end up with lots of reactant. And this just defines shifting, which we've already talked about. Shifting, a system is said to shift when it moves from one equilibrium position to another equilibrium position. Systems shift in response to a change in conditions. What do we call a change in conditions? That is called a stress. While a system is shifting, are the concentrations staying the same or are they changing? To get from here to here, during the shifting process, were the concentrations staying the same or were they changing? They were changing, okay? So while the system is shifting, the concentrations are changing. Are we at equilibrium while we are shifting? No. Once a system is finished shifting, then the concentrations of reactants and products will again remain constant. So we will be at a new equilibrium. Yes.
Can stress make products like make the species reach equilibrium faster or
No.
no?
I mean, honestly, I don't know. That would require some fancy kinetics, like math, I would think. Because temperature is going to make the rates speed up, but it depends how much you change the temperature, I would think, right? Because changing the temperature is also going to make it shift, and how far does it have to shift until it's at equal, you know what I mean? So I would think that increasing temperature would probably make it get to equilibrium faster. That is not something we need to worry about in grade 12 chemistry.
Okay.
Okay? The only thing that you need to know that gets you to equilibrium quicker is a catalyst. Okay? Once a system is finished shifting, oh, we already talked about that. Never mind. Closed systems, we already talked about these last day. Remind your partner what can go in and out of a closed system and what can't go in and out of a closed system. Okay, so let's remind ourselves. In an open system, mass can go in and out, heat can go in and out. That's an open system. In a closed system, mass is stuck. It is stuck inside, and that is it. But the heat can go in and out. Okay, energy, kinetic energy. Well, that's the kettle. I'm like, what's making that noise? It sounds like a kettle. Look, oh, it is the kettle. Okay. I hope this is obvious. We've sort of done this at this point. If the forward reaction is endothermic, the reverse reaction must be exothermic. How many people heated a hydrate last year? Some of you. Many of you did, probably all of you did it and you've forgotten, I'm guessing. Okay, if you were in my class, we heated copper sulfate, hydrated copper sulfate, because it is a lovely blue color. Okay, this is blue. And copper sulfate, what is the formula for copper sulfate? CuSO4, it's copper 2 sulfate. There we go. So it's CuSO4. Now, if you have a hydrated salt, it means that there are water molecules embedded in the crystal lattice. Let me see where my crystal lattice is.
Oh, you did the dot and the T.
There we go. And for every one copper sulfate, there are 5 waters. Does anyone remember how to put those 5 waters onto this formula? Dot. And then 5H2O. They're embedded in the crystal structure. So what might that look like? I've only got 2 hands, so I can only put in 2 water molecules. These are going to be my water molecules because they kind of look a little bit like water. They got 2 things, right? 2 H's, and then the bottom part, 1 O, all right? And there they are embedded in the crystal lattice structure. You see how there's space for them there? Yeah? What kind of force is holding the 2 ions to each other? Ionic bonds. Absolutely. They're ions. What's holding the ions together? Ionic bonds. Yes. What is holding the water inside the crystal lattice? Not hydrogen bonds, but intermolecular forces, which is the more generic term. A hydrogen bond is a type of intermolecular force. Okay, in this case, I would assume it would be an ion dipole interaction, but you do not need to know those names. You just need to know that it is an intermolecular force. What is stronger, ionic bonds or intermolecular forces?
Oh, covalent strong.
Covalents are strong. Ionic is strong. Intermolecular forces are relatively weak.
I thought ionic was
Okay.
It dissolves, right? It dissolves.
It dissolves, but it dissolves because taking the place of the strong ionic bond is a lot of ion dipole bonds. So here's my dipole, here's my ion. So we replace that with a whole bunch of those. Plus, we're increasing, when we take this apart and these particles are now moving freely, we've also increased the entropy of the system, which nature also loves. Nature loves increasing entropy, randomness. Okay? So, and there are salts that do not dissolve to any significant extent. So if you take chalk and you put it in water, it just sits there. Yes? So not all salts are soluble. It just depends on, some ionic bonds are stronger than others, but in general, ionic bonds are stronger than intermolecular forces. In general, okay? And if you're interested in seeing the kilojoule values on those, the energy of each of those, I do have a little chart if you ever want to see it. Anywho, so we heated this last year. We put it in a crucible. I'm going to draw a little crucible over here. You do not need to draw this. This is my lovely drawing skills here. Okay, so the crucible looks something like that. And it had a lid on it that looked something like that. Anyone remember that? Does that ring any bells? Did we not do this? We must have run out of time. Were you first semester? Second semester. How did we not do this?
I think we were just so slow.
Seems very weird. Anyway, we would put our blue stuff in there, and then we heated it on the Bunsen burner. Yes? So we heated on the, that's my fire, okay? I know, I cannot draw. It's sad and terrible. But as the water leaves, and the water will leave because the particles will start moving, everything will start jiggling faster and faster and faster until what? The water evaporates right out of the crystal. And now, after the water has gone out, it ceases to be blue and it becomes white. Because copper 2 ions need the interaction with the water to become blue. Don't ask me to explain it. It has to do with D subshells and things like that. No, I don't know. Okay? So, we heat it, it becomes white. That process, because we had to heat it, what kind of process is that? That is endothermic. Now, after the experiment, what we did is we took an eyedropper, okay, the eyedropper, and we put some water back in. Anyone remember what happened?
I do not remember.
No, we didn't do this. Okay, it turned blue. Okay, it turns back to blue, and it gets hot. So it turns blue and it gets hot. And that's because, why does it get hot? Because that is an exothermic process. And if you think about it, when the water comes back in, are we breaking forces or making forces? when the water comes back in. We're making forces, and remember, bond formation or intermolecular force formation is always exothermic, because it is more stable when it is like in its like little happy positive is near negative state. Okay, so we have Cu, SO4, solid, plus 5 H2O liquid, but you can make it go backwards. Okay. There's a recap here, but I don't know that we need the recap. I think we've sort of hammered this all home to death. Some. Okay, there's some exercises here, which we're not going to do. We're going to, actually, before we do that, we're going to do a little demonstration. Okay. Everyone's going to stand up. Stand up. Stretch over to one side. Stretch over to the other side. Stretch high in the air. If you have room, you can put your arms, like sort of stretch them backwards as much as possible. Oh my goodness. And then we're going to shake out our arms. And then we're going to touch our opposite shoulders. Okay, and then we're going to do the same thing behind our back. All right, and then we're going to pat our head and rub our tummy. And then we're going to pat our head and rub our tummy the other way. And we're going to shake it all out, and then we're done. We're going to sit down. Okay, now I have here 2 tubes. Okay. It's not bromine. They made us get rid of our bromine. They're like, it's too dangerous. It looks like bromine though. Yeah. What's in here? You don't need to tell me the chemical, just describe it. It's a gas. Yes. It looks like bromine. What do you mean it's a gas? Is it a gas? Could it be a liquid? Is this a liquid?
Oh, I genuinely thought that was like orange.
Oh, maybe. It's really cool.
Yes.
Yeah, we don't like it.
Can we like smell it?
No. It's actually a toxic gas. So we don't want to smell it. And besides which, you know, we'd have to then replace the gas. Okay. But it is a gas. What color is it?
Like brownish.
Brownish, orangish, orangey brown. Yes. And now, oh, we have just boiled some water. So I'm going to replace my old boiled water with some new boiled water. She's pouring boiled water. It's like she might be making tea. Good Lord. Okay. And I'm going to take this formerly ice water. And I'm going to add more ice cubes to it so we have new ice water. I'm just going to go grab those from the freezer. Oh.
Ice with a chocolate.
Yes.
Remember when ice bucket?
Yes.
Yes.
I can't remember. I think.
I recorded it.
You did Mr. Co, yeah. Okay. These trays are just dying. I want to equilibrate the temperature. So I'm giving it a good slosh. Will you go in? Huh? We're good? Okay. All right. Now we're going to look at this one here. All right. And we're going to watch and see what happens when we put it into the cold water. Now, before we put it into the cold water, let's take a look at these two tubes against the whiteboard. Do they look the same? No, which one is lighter? This one is lighter? Okay, this one is lighter. I'm going to keep holding it here for comparison. This is the darker one, right? Oh. Oh. Okay, so the darker one is now this one. So what could you say about the concentration of brown gas in here and the concentration of brown gas in here? Which one at this point has a higher concentration of brown gas? This one has a higher concentration of brown gas. Yes? Now, this just went into the hot water. Now, which one has a higher concentration of brown gas? This one. That begs the question, where did the extra brown gas come from? And then, where does it go? Is it a change in state? Well, let's take a look. Let's see if we have anything else in here. Okay, I'm just going to grab some paper towels so I can get rid of the water by the water on the outside. Okay, so this has been in cold. No liquid, not a change in state. So we're like, where did the brown gas go? And now,
Where did it come from the top?
where did the brown gas come from? So in this flask, we have some brown gas. Pardon me?
The change in the color starts from the top.
Does it?
Yeah.
Does it? This is lighter than that. This is lighter than that is. Here, I'll put it just at the bottom. Yeah? Okay.
But if you put it in like the cold, it's also more like colorless, right?
Pardon me?
It's also like colorless. You put it in the cold.
What about colorless?
Really, really cool.
I am interested in the word colorless.
Transparent.
And the reason I'm more interested in the word colorless is that there has to be something else in here, yes? What else could be in here? Another gas. What does that gas look like? Colorless. So it looks like nothing. Now, when I put this into the pot, what is happening to the colorless gas? Is the colorless gas changing color? No, because it's colorless. Its property is colorless. It's reacting and turning into what? Brown gas. Yes? Then when I put it into here, what happens to the brown gas?
Lighter.
The brown gas gets lighter. It reacts and turns into the colorless gas. Okay? Now, has this changed temperature at all? Or sorry, changed color at all while we've been sitting here? This one that hasn't been? No. So we have a closed system. It is at a constant temperature. We're not stressing it in any way. We're not changing any conditions. We are at equilibrium. Once this has sat in the cold water for a while, eventually it stops changing color. So we have reached a new equilibrium. And then when we put it in the hot water and leave it for a while, it would be better if I could immerse the entire thing in hot water, but I don't have a container big enough. Okay? We are now at a new equilibrium. All right? Let's take a look then at what this equilibrium system actually looks like. I know. So we have some N2O4, and we have some NO2. The NO2 is the brown gas. The N2O4 is the colorless gas. And let's assume that initially I put some N2O4 in my container. What does that tell us about our forward rate? Forward rate is fast. What does that tell us about a reverse rate? Our reverse rate is 0. However, it is in a closed system and we're not changing the temperature. And so what's going to happen? Yes, it will reach equilibrium. So at 4 minutes, we have reached equilibrium. Now, there's a lot of blah, 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 blah here. So we're just going to move on past that. Ooh, here's a good question. Dynamic, this is on our next page. Dynamic means changing. What is changing in a dynamic equilibrium? Is it concentrations? Are concentrations changing in a dynamic equilibrium? No, because remember, concentrations don't change. You're forming product at the same rate as you are using it up, so you're not going to change concentrations. This is no. Is it color? Whoops, I can't spell color. 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 Is it color? This is at dynamic equilibrium. Is it color that is changing? No. Is it rates that are changing? No, because they're equal, right? And the rates are staying the same. If they were changing, then we'd have not be at equilibrium anymore. What is changing? Products and reactants will be at different concentrations from one another, yes. Okay, unless you get some like weird thing where they're exactly equal, but that's like a random weird coincidence. Okay, yeah. Yes, potential energy. Well, we have the same concentrations of products and reactants, and they all contain the same amount of energy, so as they did before, so no. Jonah? The particles, yes. Individual particles. And why is that? Because individual reactant particles are changing into products. Individual product molecules are changing into reactants. So you have change at the particle level, but at the macroscopic level, you see nothing. Since the forward and reverse reactions still occur, but there's no observable change, no change at the macroscopic level. So you can think of this as like the little molecules in here. Have you guys ever done square dancing in PE? And you're like changing partners all the time? Yes? In here, there's a square dance happening. Yes? And all the little partners, they're like dancing and they're crossing over and they're moving and changing partners and do-si-doing and doing whatever the heck it is that they do. Can you see any of that? No, because they are too itty-bitty for us to see. Yes? So change is happening, but not at a level where we can see. All right. We've already talked about this, but macroscopic means large scale, visible, observable. Can you think of some macroscopic properties? Mass, color, what else? Temperature. Volume. pH. Huh? You cannot see it, but you can measure it. So it's a macroscopic property. Yeah, it's measurable. Yeah? Skate. State. Thank you. The amount of solid? Yeah. Okay, all of those are macroscopic properties and they all remain constant. So we could also include concentration in there, even though we can't really see it. Macroscopic properties, concentrations, some of them we can measure. Total pressure, color, temperature, density, pH. You don't really need to be able to make a huge list or anything like that. You just kind of need to understand what macroscopic properties are. And if we made no changes to this system, it would just sit here forever, looking just like this. But what would be happening down at the particle level? Mad square dancing, okay? You know, do-si-do, whatever it is. Have you guys seen the Bugs Bunny cartoon where he like has these little hillbillies and he like calls the no?
This is a niche reference. I don't get it.
Okay. Never mind.
Okay, but
I grew up on Bugs Bunny cartoons.
yeah.
I might show it to you at some point just because it's quite funny. On the other hand, I have to check because Bugs Bunny came from a long, long time ago. And sometimes you find things in there that are horribly racist. So like, I'm like, oh, I realized the other day that there was an expression that came from it that was like in my vernacular, like when I was in elementary school and stuff. And it was just horribly racist. And I was like, oh. And then I said it the other day because I guess I'd been thinking about it, right? So it was in my head. And then I said it, and then I'm like, oh, anyway, it was horrible. Anyway, there we go. What was it? You don't want me to say? Okay. If you would like to know, I will tell you later. I'm not going to say it on YouTube. Okay? You can come and ask me later. It's not that bad. I mean, it's not like the N-word or anything like that, but it is really offensive. Okay? Okay. So here are a few things that we consider before we summarize anything. Changing the temperature will alter the rates because we know changing temperature changes rates. And changing the temperature changes the rate of the exothermic and endothermic reactions differently. It will, so if we increase temperature, both rates will do what? Both rates increase. But one rate will increase more than the other. If we decrease temperature, what happens to the rates? Both rates are going to decrease because that means fewer collisions, right? And less energy in our collision. Both rates decrease, but one rate will decrease more than the other. The endothermic is always affected more by both the increase and decrease in temperature. We know that to be at equilibrium, the temperature must be constant. We know that we must be in a closed system. Now, this seems kind of crazy to actually bother saying it, but you can approach an equilibrium starting with only reactants, or you can approach an equilibrium starting with only products. It doesn't matter, okay? So equilibrium can be approached from the left or from the right. And we don't have enough time to talk about that today. We'll do that next day. Here are 6 characteristics. I'm going to let you read them on your own. Your homework is pages 9 to 10, 9, 10, and 20 to 23.